Thanks a lot for allowing me this opportunity. It's been some great briefings so far. Looking forward to the rest of the day. My research basically is impacts of cognitive decay and memory recall during long duration spaceflight. And let's get into it. See here. In my agenda, basically, I'm going to talk about the project, the knowledge gap, the research problem, the experiment segments, the methodology, the realism, conclusions, and sources. A lot of material covered in a few minutes. So basically, my project is looking at 32 subjects possessing very similar backgrounds and educations. They're going to be wearing an EEG, a portable wireless EEG, while they fly drones and do other cognitive tasks. Once the data comes in, it's going to be processed through MATLAB, EEG Lab, eLoretta, NeuroCoach, and some other tools to give us a predictive neurocognitive profile. Ultimately, that profile will lead to what we call what's commonly known as Rasmussen's taxonomy, meaning where the brain is in its behaviors, whether it's in skills mode, rules mode, or if it's in knowledge mode. And I'll tell you more about that in a minute. The knowledge gap itself is until we leave the moon's orbit, NASA's Mission Control Center has always controlled or managed the spacecraft. The astronauts have always had very little work that they've done as far as piloting or controlling the state of health and repair of the spacecraft. On the ISS, the Mission Control Center still does that, and they tell the crew up there when it's time to replace an LRU, a line replacement unit, pull out one system, shove in a new board, and then send the broken piece back to the Earth for repair or disposal. Now, once we go beyond the moon, communications latency is not going to allow that to happen anymore. The crew itself has to be autonomous. To become autonomous, think about all the knowledge that is currently housed in the Mission Control Center right now by 100+ controllers. All that knowledge and experience and past lessons learned needs to be on the spacecraft in some form or fashion. And part of that's going to be the next generation artificial intelligence. If you can think a kinder, gentler HAL 9000, we can never get away from that reference. And the astronauts themselves. Currently, NASA trains all astronauts to be at 100% ready at all times. We know that that is not feasible. But they do that. So the astronauts are in a constant training mode, and it's a very expensive training mode. So the problem is that future long-duration spaceflight will expose the crews to prolonged microgravity, cosmic radiation, and other stressors while living and working within an isolated, confined, and extreme environment. One thing that we've never experienced, and you can think about this, is the crews, when they get beyond the moon or shortly beyond the moon's orbit, they're going to look back in their virtual rear view mirror, and they're not going to be able to see Earth anymore. So that concept is called out of view, Earth out of view. And that's something that they'll then know there's not going to be an emergency return, quick return, and there's going to be no rescue if there's an issue. They're going to have to go to Mars, turn around and come back in that low energy trajectory. So the research problem, such factors are expected to negatively impact the body's central nervous system, the cognition, memory, and behavior. And then research is needed to comprehensively measure, model these behaviors and memory decay, recall. Ultimately, it comes down to, and my computer's just doing this, ultimately it comes down to how often will the crew need to train? They're going to have a very autonomous spacecraft. There's going to be and I'm military in Space Force, and we always say that our job is 99% boredom, followed by that 1% of terror. When a spacecraft or space satellite doesn't perform as it should, that terror, that 1%. Same things for we expect with the crews going to Mars and beyond, is that the crew, the spacecraft is going to be very autonomous. The crew will have to do very little initially, or at different stages. So how often should they train? And then all of that data, all of the information that they need to house, what do they really need to train before they leave, and what can they train en route? And those are big questions. So ultimately, there's multiple segments to this. So research test subjects that here on Earth that are reflective of future astronauts, realistic spaceflight activities, cognitive tasks, trained, practiced, and baselined. So this is, I'll show you a list of tasks that my crews are doing. And ultimately, well, and allow time, you need to allow time for natural forgetting that occurs over time. That's the forgetting curve. We call it the training and learning curve. And then realistic analog facilities. So I have an analog I'll show you that is realistic. Our crews go in, the door's locked, they don't come out. Test subjects, test the subjects during task performance. That happens with an EEG system, a portable EEG system I've developed, and cameras, audio, so we have triggers. Record the EEG waveforms, go back. Then we process the waveforms. We measure the performance using Rasmussen's skill rule knowledge taxonomy. We seek correlations. We determine statistical significance. We report on that, and then I document the findings, and hopefully I graduate. Okay, so back to the methodology. Again, 32 students, 32 subjects. They're participating, and they'll also have questionnaires. I've already said all this. So the tasks themselves, this is just a short list. Well, this is a list of tasks. Not all of these will be used. And I'll tell you, I just finished one mission and I just finished analysis. So I'll give you a real short update in a second. But the Tower of Hanoi is a cognitive motor task that they'll do. If you've never heard of that, that's the it's a little puzzle, 3 rungs and 9 rings, and then they're building a robot, a rover. They're building an artificial intelligence Raspberry Pi. The drone operations, they're going to do that several different times, and ultimately in the mission that just concluded, the drone was the premier task that all of the crew did and enjoyed, and it gave me the most data. So ultimately, in my next crew mission, which starts October the 7th, they're going to be doing nothing but primarily drone tasks. They'll go outside in a spacesuit, they'll fly a drone and come back inside. And I'll show you more about that in a second. Okay, so here's the facility. This is up in North Dakota. It's called the Lunar, or the Inflatable Lunar Mars Analog Habitat. It's about 15,000 cubic feet of facility. So it's a really large facility. 5 modules. The crew gets to wear, this is a prototype suit and a prototype electric rover. The habitat includes modules for maintenance, vegetable cultivation, physical fitness, human performance, and geology. This is the EEG system that I've developed, put together with parts, either COTS, commercial off-the-shelf parts, or built boards that we've put together. One of the lessons learned is this system is about 4 pounds, so it has to be tethered at the back of the space suit. And I've got another photo coming up of that in a minute. Otherwise, it pulls the head back, and that's just not a good thing. But what we're looking for here is I'm measuring the brain's transition between networks. When you're presented a task, when you're presented a task, your brain goes into a modeling function, and it says, have I done this task before? Have I seen this model before? And if you have, then your brain says, here's what you do, and here's the decision. If you haven't, then your brain goes into other modes that learns or selects the best outcome. And so what I'm measuring is that transition between those modes, how fast that transition occurs, and then whether or not you even transition at all. Oh, so the benefits, basically by determining cognitive rates, we'll have a better understanding of state of knowledge and when refresher training is really needed. But this is not just for space. This is on Earth as well. Outcomes will help pre-flight training design, will provide a supportive evidence to medical and other industries that treat TBIs, dementia. There's a whole host, depression, anxiety. Being military, I spent some time over in the desert, and I came back and I have PTSD. So we'll be able to treat a lot of those conditions if you understand by training, with training, if you understand when you need to provide the training and to what level of detail of training. Lastly, we'll provide these tools to industry as well for predicting cognitive decay and memory recall. And then there's sources, and I've got a lot of sources. So if I can give you just a real quick, let's see, I've got about a minute and a half now, update on this mission. So here we go. This is a couple of pictures here. This past May, we had 8 subjects. I had 4 subjects that were inside the facility for 21 days and 4 subjects as a crew, as a control group that were outside. All of them completed the tasks. They all wore EEGs during the tasks. And some of the outcomes that I'm actually building a briefing that I gotta give to my committee this next week is that we made the EEG a lot, well, I made the EEG a lot more comfortable to where it's a lot less complicated to put on, because if you can imagine putting this cap on with 32 electrodes, you have to get it in the right place. These are all dry electrodes. This can be worn inside of the crew helmet, which has never been done before. And then they're flying a drone, which they had never done before. So they were trained, given some time to forget, and then tasked to do the tasks, recorded, and then analysis was completed. And all of this, all of the analysis is just now finishing, and with this briefing this week. So it's been a very exciting couple of years. This is my PhD work, and come to find out, very little of this has ever been done before. So it is exciting to see it come to fruition. You can see that's the EEG going into the spacesuit, and also to the EEG when you sit down to do a robotic task. So in saying all that, I've got a little, about 14 minutes. So questions, be glad to answer. And thank you very much for your time. Any questions? Please.
Sure, Terry, I'll ask a question. It's really interesting. I was just wondering, you mentioned the electrode, what you call it, sort of cap moving around. How sensitive is the data, quality of the data you get to that movement, and how strictly does it have to be exactly in the right place? I guess that's one of the challenges you mentioned.
And that's a very good question. With 32 electrodes, and one of the fallacies too is understand that every one of those 32 electrodes is receiving the same signal. My background is RF. I'm an RF engineer. So, but it's a timing difference. It's a Doppler and timing difference in those electrodes. So once it's in, it doesn't have to be exactly with this system, because these electrodes are also amplified. They're also shielded. That was one of the other lessons learned is, oh goodness, where'd it go? This is a board inside of a case that I had to do afterwards because of shielding. It was so much noise. And this is the board that I've still got to populate to give you an idea. But you can see there the boards weren't shielded, and that was a lesson learned for me. But to answer your question, it doesn't have to be exactly. it's really the post-processing that I do to clean it all up. Getting rid of the noise, and there's a lot of great software out there. This EEG lab is an excellent tool for that kind of work. If I'd had another week or so, I could have really showed you some outcomes that were amazing, because with this one person here flying a drone, I can see when she went to make a decision, and then I could see her execute it all within 500 milliseconds on the computer screen. I just couldn't mark it fast enough, so that was the software that has to do that.
Yeah.
But it's typical RF signal processing. MATLAB does some really great work. Any more questions? Well, again, thank you for the time. I'm excited to talk with a bunch of folks that are in the same areas of research. And so it's just a motivating thing for me going back to work tomorrow.
Yes, Terry, this is phenomenal. It's really wonderful research you're doing and presentation. And there's so many biomarkers that arise related to the brain and our neurological system that could really be help support your research and a lot of tests to do as well.
I have 3 more missions. Each mission is going to have 16 people. I'm sorry, 8 people. 4 that go into the habitat for 21 to 30 days, 4 on the outside. And each one just adds more. It's a repeated measures research, so that just adds more data to it. NASA has not done this before. The closest thing they've got is something ongoing right now, where they use nursing students, and I'm in discussion with NASA to get these same systems on orbit when they finally start letting experiments go back up there. But that's probably 4, 5, 6 years down the road before they decommission the ISS, hopefully. But thank you very much. Appreciate it, everyone. And please, my contact information, if you got any suggestions, questions, help me. I'll gladly support you as well.